The topics today I'm going to cover is first of all the Bernoullis trials, its generalization, then comes the normal approximation, and the final is the Poisson's approximation, and along with it relevant examples will be covered. Now, starting off with the Bernoullis trials. First of all, suppose say there are n objects. These n objects can be arranged in n factorial ways, which is we already know. Now suppose say we have k objects which are to be selected out of n objects. K is smaller than n. This k objects can be selected from the n objects, and this is given by n combination of k, which is equal to n factorial upon n minus k factorial into k factorial. That is, we have selected k objects out of n. Now, once we have selected those objects, in order to arrange those objects, n c k is equal to n factorial upon n minus k factorial into k factorial. In order to arrange these objects, we have selected k, and therefore those can be arranged in k factorial ways. Multiplying both of them, n c k, n combination k into k factorial, which is equal to n factorial upon n minus k factorial into k factorial. K factorial goes, and we get n factorial upon n minus k factorial, which is nothing but the permutation n p r, permutation. Now, let us take an event event A. Probability of occurrence of event A is given as, suppose say P, and probability that the event A will not occur is given by say Q, which is equal to 1 minus P. Now, out of n number of trials of an experiment, A occurs k times, which simply means that A dash occurs n minus k times. Therefore, probability that the A occurs in specific order is given as P raised to k into Q raised to n minus k. Now, out of n trials, A occurs k times, which means that all the A events are identical amongst themselves, and therefore it is given as n factorial upon k factorial into n minus k factorial, which is nothing but n combination of k. These event and the previous event are both mutually exclusive, and therefore the probability that A occurs in any order is equal to n combination of k, p raised to k, q raised to n minus k, which is nothing but the Bernoullis equation. Now let us consider an example. We roll a dice, say 5 times. What is the probability that we get 6 exactly 2 times? In order to solve this, the probability of occurrence of the event, that is probability of A, that is the event A, we get 6, which is given as 1 by 6, because the dice has 6 faces and occurrence of each face is 1 by 6. Probability of occurrence of each face is 1 by 6. Therefore, this event occurs twice, and therefore its probability is 1 by 6 raised to 2. But we have 5 trials. Therefore, in the other 3 trials, the other events will occur. That is probability of a 6 bar. This will occur other 3 times. Total number of trials is 5 factorial, and we have 2 factorial and 3 factorial in the denominator, which is nothing but 5 factorial upon 2 factorial into 3 factorial, 1 by 6 the whole square, and this is nothing but the occurrence of the other events except 6, which is 5 by 6 the whole cube. This is the probability of occurrence of 6 exactly 2 times. Now let us have a look at another example. Similar example. We roll a dice 5 times. We want the probability that 6 occurs exactly 2 times, 5 occurs exactly 2 times. What is the probability? First of all, the probability that the event A, that is the 6 will appear on the dice, is equal to 1 by 6. Similarly, the probability of event B, that the 5 will appear on the dice, is equal to 1 by 6 again. Each event has probability 1 by 6 since we have 6 faces on the dice. Now, this event of occurrence of 6 occurs 2 times. This occurs 2 times. We have total trial that is equal to 5 trials. Therefore, in other 1 trial, the other events will occur other than A and B, which is equal to 4 by 6. Therefore, now the probability can be given as P, that is equal to 1 by 6, which is the probability of the occurrence of event 5, of getting 5 on the dice, which occurs 2 times. Similarly, 6, which occurs 2 times, and 4 by 6, which occurs only 1 time. Total number of trials is 5, it's 5 factorial, and 2 factorial into 2 factorial into 1 factorial. This is the answer for that particular event, and is the probability of occurrence of 5 and 6 2 times each. Now, From this we can get the idea of the generalized form of the Bernoullis trials. Therefore, the generalized form of the Bernoullis trials can be stated as probability of event k1, k2, dot 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 k r, that is equal to n factorial upon k1 factorial, k2 factorial, dot 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 kr factorial into probability of 1 raised to k1, probability 2 raised to k2, dot 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 probability r raised to kr, which is nothing but the generalized form of the Bernoullis equation. Now, going into the concept of normal approximation. We derived Bernoullis trials as n k, p raised to k, q raised to n minus k. For normal approximation, suppose the number of trials that is equal to n is very large, that is, it tends to infinity, and p is, say, fixed, and k is in the under root npq neighborhood of np. Then we get the approximation as n factorial n combination k, p raised to k, q raised to n minus k is equal to 1 upon under root 2 pi npq e raised to minus k minus np the whole square upon 2 npq, and here p plus q is equal to 1. This is the normal approximation for n very large, that is, n tends to infinity, and p is fixed. Let us understand this by an example. The approximation also works satisfactory for the intermediate values of n, and so in this example we will take an intermediate value of n not too large. Example, suppose, say, n is number of trials is equal to 10. Probability given is 0.5, that is the probability of the suppose, say, in this example n is equal to 10, p probability is equal to 0.5, and k is equal to 5. Therefore, the probability can be given as n k, p raised to k, q raised to n minus k, which is nothing but 10 combination 5, 0.5 raised to 5, and other 0.5 raised to 5, which gives us answer as 0.246. Solving the same example with the approximation, we get p of k is equal to 1 upon under root 2 pi npq e raised to minus k minus np the whole square upon 2 npq. Substituting the values, we get the answer as 0.252, which is much similar to the previous answer, that is 0.24, much closer. Therefore, the approximation results is much similar to the Bernoullis trials equation results. And now taking the discussion further to the approximate evaluation of this case, approximate evaluation of P, where K is between K1 and K2. Which is equal to sigma n p n c k, which is the n combination k, p raised to k, q raised to n minus k, and summation is from k1 to k2. It is equal to, approximately equal to g of k2 minus np upon npq under root minus g of k1 minus np upon under root npq. Which is the approximate evaluation when K1 and K2, K is between K1 and K2. Here we should note that NPQ is very much greater than 1. That is, the value of N is very large. NPQ is very much greater than 1, which is the important thing that we need to take care for the normal approximation. Now, taking our concept further to the Poisson's approximation, which is the last part in our discussion. Poisson's approximation. Now, normal approximation was valid for the conditions n is very large. N is very large, that is, the number of trials are very large, and P is fixed. P is fixed. Therefore, NP is greater than much greater than 1. NPQ is very much greater than 1. These were the conditions for the normal approximation to be valid. But what if we have a different case wherein, suppose, say, P tends to 0, or suppose, say, P tends to 1, that is, probability tends to either 0 or 1, or say 1 minus P, that is equal to Q tends to 0 or Q tends to 1. What in that case? In that case, the normal distribution or the Gaussian curve tends to deteriorate, and the representation completely fails if P is equal to 0 or P is equal to 1 or Q is equal to 0 or Q is equal to 1. The representation completely fails. That is, the distribution is no more a normal distribution. What happens in that case? In that case, what is the probability? So we will now look into that. For that comes the Poisson's approximation, where if p tends to 0 and n tends to infinity, then np is equal to lambda is some definite number or some fixed number. It is some fixed number, that is p tends to 0 and n tends to infinity. N is very large, p is very small, and the multiplication of both of them gives us a fixed number, say lambda. And the distribution, there's a proof, and on proving this we get the distribution as which is below. P tends to 0 and n tends to infinity are the important conditions that are to be taken care of, and np is equal to lambda. We get the distribution as n factorial upon k factorial into n minus k factorial, which was our initial representation, that is the initial Bernoulli trial representation, p raised to k and q raised to n minus k, which is approximately equal to e raised to minus lambda raised to k upon k factorial as n tends to infinity, which is nothing. This is nothing but our Poisson's distribution. That is, the probability is nearly equal to the distribution, nearly goes equal to the Poisson's distribution. If p tends to 0, it is no more a normal distribution, and therefore comes the concept of this Poisson's distribution. So this is all for the entire presentation, and thank you. My name is Jay once again. Thank you.